here with us now we have Renaud and Dina from Sevensense, and they'll give us a great presentation about what they do at their Zurich-based startup.
Should I go? Yep. Great, so good evening, everyone. Happy to see you here, and thanks for joining. Also, thanks for the organization. So I'm together with Dina, and we're happy to give you our talk titled Inside the Robot's Brain. So Dina and I, we worked at Sevensense, which is an ETH spin-off. It's based a few blocks down the street, and it's a company that builds the eyes and brains of autonomous robots. So here you see Marvin. Marvin is an autonomous cleaning machine, which is developed in partnership with our customer Vetrock. And here you see a video that was recorded at the startup days earlier this week in Bern. And here we taught Marvin to drive a path, and then the robot can repeat that autonomously. So cleaning is one of the industries where we believe that robotics can have a positive impact for our society. So you also see here logistics, outdoor delivery, and also healthcare. What we want, our goal is that robots work together with humans in such scenarios so that they can alleviate dull and repetitive tasks for the workers. So here, for example, in the healthcare, the healthcare personnel spends a lot of time only carrying goods around, and we want to support with this task so that they can spend more time with the patients. And here you see where robotics is today, so very structured, very rigid environments in factories, so there's not too many humans driving around. You can also modify the infrastructure so to make it easier for the robots. And our goal is to bring it to the right, so in much more dynamic spaces, for example, the Zurich Hauptbahnhof, where you need to drive in crowds, you need to drive with humans. And also we want the robots to be able not to drive only inside, but also to go outdoors.
So as Renaud just mentioned, our goal actually is to not only to have the machines as we have them right now in structured environments like industrial setup, but we want them to bring them in more dynamic environments that we see in our daily life, like in hospitals, in train stations, in airports, in grocery stores. And our mission at Sevensense is basically to make the machine behave more like humans so that we can bring them into those environments. So in order to reach this purpose, we need the machine to have sensors which act like human eye. We need them to have some sort of wheels in order to perform some motion. And most importantly, we need to have them to copy our reasoning logic that happens in our brain without thinking a lot into the machine so it can behave more like human. So this copying the brain process, we call it robot brain life cycle, and it answers 4 questions that we usually ask ourselves every day, and we answer them without even thinking about them. So these 4 questions is where I am right now, what can I see in front of me, and given this to input, what is the best way for me to move in order to perform certain tasks, and lastly, if I know what is the best way to move, I want to execute this motion. So if we want to say it in a more technical term, this constitutes of 4 modules. First is called localization, then mapping, then motion planning, and lastly control. And in the next slide, we will dive deeper into each one of them.
Starting with the localization part, so here we want to allow the robot to know where it is in space. So with this, we start with the eyes of the robot. So that's a multi-camera sensor that we built in-house at Sevensense. So here I have the dev kit with only 5 cameras, but you can connect up to 8 cameras. You can put these cameras all around the robot and give it a 360 degrees view of its surroundings. So not only the 2 eyes to see in front, but can also see on the sides, behind, and also look at the ceiling. Also with this sensor, we have an IMU, which is an inertial measurement unit, which measures forces and velocities, and it's something similar like the inner ear in the human body. And all this sensor we developed in-house, so we have full control of the electronics inside, and that allows us to produce the best quality data that we can then use to position the robot. So maybe a question for the audience. Does someone know what is SLAM? Great. Correct. So SLAM, simultaneous localization and mapping, it's basically the process of estimating jointly the position of the robot in space along with creating a 3D map of the environment. So it's a very interesting problem. And here at Sevensense, we use, as I said, the cameras to achieve this. So we start by extracting key points from these images. These are the green circles that you see here. And by tracking these key points among different frames, we can do triangulation. And that allows us to estimate the movement of the robot. So these key points are detected looking at gradients. So usually you have either edges or corners in the image. How we do this exactly? So you see at the right, we have one of these image patch that is extracted around one of these key points. And then this we compress in a set of features, so a vector of values that are then stored in the database. In this case, it's our 3D map. And then by retrieving these descriptors, we match key points between each other. And that allows us to find association, as I said, between the images. So this can be used, as I said, to estimate motion. So I could take the sensor, walk along the room, then I will come back here, but there's uncertainty involved in the process. So even if I come back here, the robot or the sensor might think it's actually a bit to the left. And then we have a concept called place recognition that allows us to close the loop here. So basically comparing images that were recorded at the beginning and ones that were at the end, we find associations, and then we can correct for the drift. So once that we have a map of this environment, any robot can load this map and then localize itself in this map. So that's what we call global localization. And finally, we can use the same matching procedure to merge different missions or merge data collected by different robots. So that would allow us to create a unified map representation. Some examples of such correspondence, so all these green lines here are associations between these features. In this case, we used machine learning techniques to extract better descriptors that are more powerful and that allow us to match images with different viewpoints and also with different type of illumination. Here we show one example of a mapping session in a big warehouse, so roughly 100 by 200 meters. Here we did 11 different sessions that we then, using the same associations, merged all together in this map. And this is the final result. So it contains roughly 100,000 key points. And then any robot can load this map. We can place the robot anywhere in the environment, and then the robot will be able to know its position. So then the robot can do its task, and once the task is complete, we can use the latest data to then update this map and reflect the latest changes. As I said, so far we're using cameras, but also some of our partners want to use 3D LiDARs for security reasons, for example. This is work we did together with Sebastian, so basically combining 3D LiDARs, which directly measure the distance or the structure of the 3D environment, and cameras together in one localization system. So what we do here is extract, in this case, segments, but similar key elements, both from the LiDAR and from the camera's images. And then we fuse these in a multimodal deep learned descriptor, and then we can achieve better localization performance. Here's one example. So again, the green lines, we show correspondences between the target map that is now below in colors. And in white, you see one such LiDAR scan. And every time you see new green lines, it's because the robot could localize itself again. This experiment was done with an outdoor delivery robot. And we also did some experiments, in that case, on the Kitty odometry dataset. So that's a popular dataset for testing autonomous driving algorithms, which was recorded in Karlsruhe in Germany. And we also did some tests in a dataset collected by some colleagues from the Autonomous Systems Lab here from ETH Zurich. And in this case, it's an underground tunnel with only little structure and also very ill-lighted conditions. But still here, this algorithm managed to localize the robot. So now that we know where the robot is in space, the next step is to understand the scene around it, so to detect obstacles that the robot will need to avoid. And for this, according to the different applications, according to the requirements, we can use different sensor modalities, so we can add sensors to our robot. So at the top left, we have a time-of-flight 3D camera that directly measures the distance. We have ultrasonics. We also have 2D lidars. And then all of these sensors can be fused together into dense representation. So here you see it's a top-down view of what the robot perceives around it. In purple, it's an area where the robot thinks it's free to go, so it's free. And in colors, you see the obstacles. So in red and green, the different obstacles that are detected. Yeah, as you see, when navigating in crowd, it's important to have a reliable detection of obstacles. But you also see that humans think that robots are pretty cool, so they try to stop them, they try to annoy them, and that also led us to the next work, which is building more advanced perception capabilities. So here with Thomas, work that we did during his master thesis, we use computer vision to basically detect the humans, to track them over different frames, and also to be able to predict their motions. So these advanced capabilities to perceive the environment allow us to have still safe but very efficient navigation in crowds.
So now that we have answered these first two questions, where the robot is and what it sees right now, it comes the third one, which is basically where to go given some criteria or some constraint. And that really depends on the mission that we want to do. So the module that answered this question is called motion planning. And as I said, motion planning can include different missions. The first one of them is called A to B planning, where we have like a start and a goal, and we want to go from A to B, avoiding obstacles. We can also have like a teach and repeat planning, like what we do with Marvin, and this is very common in cleaning industry, where the human teach a path, and then the machine needs to follow that path as close as possible while avoiding obstacles. And the third one is called exploration planning. In that case, we use motion planning actually to build the map. So we don't know anything in the environment, and we want to explore and build the map of the place we are in. And then the last one, it's called coverage planning, and this is also very common in the cleaning pattern, where we want the machine to go over all the place in an optimum pattern. So I'm going to focus in the next slides in the first two use cases mostly. So the workspace is basically the environment where the machine is, and it's usually composed of a combination of occupied space and free space. And this information we can already get from the mapping side, and the goal of motion planning is to find the poses that belongs to the free space that constitute of the path or the mission that the machine needs to do. Motion planning usually has two major challenges that it needs to solve. The first one is related on how this workspace is represented, because if you imagine the workspace is like a huge area, it contains like a continuous, like infinite number of continuous poses, like you can be in any place. But you cannot really use this continuous representation inside the motion planner to search and find the path, like the performance will be very bad. So the first question that we need to answer, how we represent this continuous space into a more discrete fashion. So how many points we need to choose, and what is the criteria for choosing those points, and how those points are actually connected to each other. So that's the first challenge. The second one is the robot degree of freedom, and I'm pretty sure that most of you heard this term, which basically is the number of actuators or joints that the system has and it needs to move. So in a simple like differential drive or a vehicle machine, usually this is very limited to X, Y, and Y, but if you have a machine that has an arm or if you have a humanoid, like the degrees of freedom increase so much, and then the dimensionality of the motion planning problem also increase, and it can be very challenging to solve. So there are two famous approaches to solve motion planning. One of them is called sampling-based, and this one usually represents the discrete environment into random points. So it relies on choosing random points, making sure that those random points belong to the free space, and then connect the random point to each other. And there are different types of random or sampling-based planning. The first one is called single query. As you can see in the first video here, the most famous one is called RRT Connect, and this one, it grows two trees, one at the start and one at the goal, and it tries to connect them to each other. The second one, it's called multi-query, and this one, it chooses like a huge number of points in the space and create something called connectivity graph. And once this connectivity graph is there, it can query the graph multiple times, and that's why it's called multiple query. The third one, it belongs to like a category called asymptotically optimal, and the most famous one is RRT star. And the idea here is that not only that we want to solve the problem fast, but we also want to optimize a given criteria of the motion planning algorithm. Like, for instance, the path length. So we want to plan fast, but also get the shortest path. So the RRT star performs exactly like the RRT connect, but as much as it has more time, it keeps improving the path. So it generates first one path, and then if it has 1 minute to plan, for instance, it will keep improving that path during this 1 minute and return the optimal path given this time. There is another approach completely to this problem. It's called search-based motion planning, and those ones, instead of those random sample, they use a uniformly discretized grid. And then do a search algorithm on top of this uniformly discretized grid in order to find the path, like something like A star, for example. And usually they generate more optimal paths, and to do that, they have something called heuristic, which is a key for the algorithm in order to know how to optimize the motion planning. So if we want the shortest path, one common criteria or one common heuristic is using the Euclidean distance. But as we see here in the video, because we have like the start and the goal are like on two corners of the grid, so what will happen that the Euclidean distance is the shortest path is going through the diagonal. And it doesn't know that there is an obstacle marked in red, like this U shape. So what will happen is that it will keep going and it will explore all the possibilities inside this U shape, which we call local minima. And then it will realize that, okay, I can't go that way. I have to go completely outside. And then it goes outside, and it takes much more time than the random samples to generate a path. So that's why this 4 or 8 connectivity graph is not necessarily good, especially if we have like a high degrees of freedom system. So then this grid becomes very huge to search. And also, even in case that we have like 3 degrees of freedom system, the possible yaws that we can have are related to the 4 and 8 connectivity graph only. So we don't really explore enough orientation of the machine, which might lead to passes that have edges. So the machine has to do really sharp turns, which is in general very difficult to follow. So the other alternative, instead of having this uniformly discretized grid, is to use something called motion primitives, which basically the person developing the algorithm on top of the machine knows like the grain of the step that the machine can do smoothly, and then the graph is constructed out of those motion primitives rather than this uniform discretization of the grid. So now that we got an idea about the different motion planning algorithms, comes the last question, which is the control. Like, okay, now we have a path that looks something like this. So we have like some discrete point sampled, and usually there is lots of space between them because it's discrete representation of the environment. So how the machine can execute that path? There are 2 modes of control. The first one is called path following, and for that one, the machine is required to reach specific poses but with no time constraints. For the second one, which is called trajectory tracking, the machine is required to be, for instance, at point P1 at time T1, and then it have like time constraints. And for that, the velocity obviously is involved because we need to compute the right velocity in order to reach the point P1 at time T1. There are 2 different types of controllers that are very famous. The first one is called PID controllers, and this is quite simple. It mostly uses the error between the current velocity and the desired velocity in order to give like more motion to the machine to correct itself and to get as close as possible to the desired goal. This is a very simple approach, but the problem is that it has so many, well, it has 3 parameters to tune, and sometimes it's very difficult to have a single tuning that works for everything. And then we have an alternative that is a bit more complex called model predictive control. And for this one, it's not only that it uses the error between the desired and the current to make the machine move, but it can also consider constraints of the problem. For example, we want to have maximum velocity, or minimum and maximum acceleration and deceleration. Or we want the machine to slow down when it goes close to obstacles. So it formulates the problem as an optimization problem, and it feeds the constraints and the error in velocity in order to predict what the velocity of the machine should be. So you'll see here, this is a visualization that we use to see what Marvin is actually doing. And this is a pretty difficult path because it has different curvatures. Some of them are very tight. What we see in arrows is the plan, and then the yellow dots are the one that the tracker is actually following. And you will see that in the curvature, it becomes sometimes very difficult to follow exactly the path. Imagine if we have obstacles, it's even more challenging. So in this video, this is a work that we have done with a student, master student, and it was a really very good work. So we were able to do A to B motion planning in a changing environment. We see here Marvin trying to keep rotating between these 3 arrows. So it will keep repeating this mission while the environment is changing at the same time. So in this video, actually, we use the full stack. So we have like the localization, the mapping, motion planning, and tracking. And the motion planner that we use here is search-based, but we used more complex heuristic than just the Euclidean distance. And also here you see in the down part, the visualization, you have in green the current plan, and in red the plan that becomes invalid because of the obstacles. And you will see here it changes, and then it knows that it has to go on the other side. And a very good thing here that because we know the problem that we are trying to solve, and we did a heuristic that is quite complex that uses the information of the obstacles plus the Euclidean distance, it's able to adapt really quickly to the changes in the environment. We'll see here it goes through this U shape. And then now this will change. It plans to go through the U shape, but then it becomes closed, and it knows pretty fast that it has to go on the outside. So yeah, this was very, very good work. This is another student work, which is navigation in crowd using reinforcement learning, which is a machine learning algorithm, where basically the machine tries to learn a policy that rewards avoiding obstacle in crowded environment. So we'll see now that the machine is able to navigate safely with human in the street. And that's another student work in exploration path planning, where basically the problem that we are trying to solve is how to choose a frontier or a point between the mapped and unmapped part in order to maximize the field of view that we have so that we can map more areas, but at the same time don't make the machine travel like super long distance while it can move closer and map more. Also, the challenge in that work was actually that the environment was dynamic. So for instance, if you are in an office and a door gets closed, what is best or what is like the optimal motion will change as well. So now just to wrap up, because I know we said so many like high technical terms, at the end what we do is related to the software engineering that everyone is aware of. So we do software development, and we follow like a software engineering process, starting with functional design to define like the use cases that we try to cover, what we want the machine to do, and then we do like high-level system design, and then also like data structure, because this is a very important aspect, the optimization of the code, because at the end the machine have very limited power, and it's important that we think how we're going to code the algorithms. And then the last thing is to do some technical class diagram, and what is very important at the end is to define some functional test cases. So it's not only that we do a unit test, but also we want to make sure that the functionality we defined at the beginning, at the end, is also working.
Thanks a lot, Dina. So as you saw today, robotics has a very wide field of applications. So as we saw, planning and control, computer vision, but also there's a lot of software development involved. And we have a great team of experts, also including people with computer science background. For me, it's a real pleasure to be working with these amazing people. And if there's anybody watching at home, then thanks a lot for the hard work. Thanks also to you guys for listening. I hope it was interesting. We're working, as you saw, quite a bit with students, so don't hesitate to reach out if you would be interested in doing a project with us. Thanks, and have a nice rest of the conference.